Hello and welcome to the future of testing with C++20. I hope you've been having a great conference so far and that this presentation will keep that trend as well. So I'm Kris. I'm a senior software engineer at QuantLab Financial. Without further ado, let's get a sneak peek into the future, shall we? So this presentation is about testing in C++. I hope all you guys and girls are, because of that, because you're interested in what the future can bring us with regarding the C++ testing. So let me just express the agenda and let's see how we'll go about it. So let's start with the motivation, why we care about testing, what's the status in C++20 at the moment, in C++ in general, why there is something to do about it, in my opinion. We'll follow it up by an implementation from scratch of a C++20 unit testing framework without any macros, and we'll leverage a lot of C++20 features in order to also leverage the knowledge of those features and how they can improve our understanding and expressiveness of the implementation. So we'll take a look into features such as modules, concepts, source location. All of them together combined give us a lot of benefits which we can leverage to implement finally a C++20 macro-free testing framework. And that'll be around 200 lines of code, which will bring us to it. After that, we'll try to push that envelope even a bit further by showing off the unit testing framework, which was based on that implementation. And it has like 2,000 lines of code of C++20, and it's a fully featured, used in production C++20 testing framework, which has a lot of goodies, which we'll take a look into in more details. I hope you will get excited about it as much as I am. We'll also compare different frameworks because the motivation will be about where we are at the moment, what frameworks we are using. So we'll compare what we have available at the moment with the UT library and see, whether C++20 give us, better performance if it comes to the runtime and the compilation times or not. Because that's also important regarding the testing, because obviously depending on how many tests you have, and especially if you do a lot of unit testing and follow good practices like TDD, BDD, you'll have a lot of them, and you will need to, and the compilation times and runtime will be actually something you care about. And we'll discuss a bit at the end whether standard is something where we would like to go for the primitives with the unit testing, or what about implementing catch using those primitives, for example. We'll take a look into that. So stay tuned for that. That will be an exciting part too. So there is a few things which it's worth mentioning, I guess. A disclaimer that wherever there will be a blue background on the slide, it means that that's something important, something to remember. It will be most likely something about C++20, which would be great if you could remember, or just something to learn out of this presentation. Since we'll have some goals to achieve whilst implementing the framework, wherever we will actually achieve them by implementing them, we'll get the achievement unlocked green background in order to boost our confidence. Also, all slides and all code provided is capable of being compiled, and Compiler Explorer Links are provided on any slide, so if you're interested in them and you want to try it out yourself, feel free to do so. Thank you, Matt, for Godbolt. So there's always a way to verify whether I'm not, trying to show off things which are not available yet. Regarding the questions, if there are any, I would really prefer to take them at the end because of the online setup. It's quite difficult to follow. If you could provide the slide number and wait till the end, I'm more than happy to answer them, and I'm more than happy to discuss anything afterwards on Discord. So without further ado, let's begin. I hope all of that makes sense and everyone is excited about what we can achieve with C++20. I said it's the future, but it's like it's 21 already. So I know it was a weird year, but let's see. So what's the motivation for the talk? As I pointed out, we would like to test something. So let's assume that we have a sum function, which just to sum, which sums the provided argument back with default expressions. Nothing really special here. C++17, simple code. How we would go about it in the current C++ without any, other facilities, libraries provided. We would probably go with like some comment or something just to, let us know that what we are doing, because we can't really put a test name on it. Maybe we could do a function name or something like that. But it's like the simplest solution possible, which probably would be a comment, and after that an assert, in which we would verify the output. Obviously, that has a lot of negatives and problems, which I will just to specify here. There is like no ability to list or run specific tests. Maybe that's not a super biggie, because if you follow a good practices like extreme programming, you always want to run all of them. But you can imagine that you would like to see what tests you have instead of comments, for example. And just for the coverage or anything related to the post-processing, that would be really nice to have. And in specific cases, you probably would like to run specific tests as well. So when you debug or when you would like to do something. So yeah, that's not great. When we fail, and here it's really important that if we use an assert, which is not great facility for testing, because it only works in the debug mode. In the release mode, will be optimized away, and since it's a macro, it'll be gone. We won't get any also useful information out of it. It won't give us too much because it's a simple facility, not really a testing facility for assertion. So not great. Solutions like that are hard to scale, integrate, and debug. It's like there's no CMake provided. There's no facilities which will make our life easier. So in the long term, it'll be hard to scale if you go like that with a lot of tests. Will make mistakes probably a lot of easier than if you would have better facilities. Because, for example, you can imagine implicit conversions. Depends on the compiler, for example. And if you don't have a good warnings and other things enabled, we may easily screw that up. As pointed out before, it's hard to follow the good practices such as test-driven development or behavior-driven development, because we don't have any functionality provided to do so out of the box. And obviously there are other things which are not great. I think like everyone understands that, just using pure C++ without any framework and our library is quite difficult for testing these days. And that's why we have a lot of frameworks provided already. There are a lot of existing solutions. There's Google Test. I think it's the most popular testing framework accordingly to some surveys. There's Boost Test provided with Boost. There's Catch2, very popular, and Dog Test, and others. There are like quite a lot of solutions provided already, so we can pick and choose. And all of them, in my opinion, are better than the solution which is provided by pure C++, which is basically nothing. However, when we look at them, those frameworks and the libraries, I believe, in my opinion, because they were written before C++20, they have some problems. Not all of them are related to all the frameworks, but some problems are related to some of them and some to the others. But I believe that we can do better, and that's why we have it. That's why this talk is about. They macro-based, all of them basically, which in my opinion is not great. Macros are just text replacements. They do not check anything which is really important from our perspective. So from perspective of the user, they might be hard to debug, hard to see what's going on. They're not really that expressive, and we don't know the implementation of them. So we can do better, I guess. They may require a lot of boilerplate. Some of the frameworks require registration. That's why the macros are handy, because they do a lot of magic, but when they fail, you don't know what's going on. So it's hard to follow. It's hard to debug because you have to step into the macros. On the other hand, when they are not macro-based, they usually require a lot of boilerplate, and it's really hard to do the expectations without macros before C++20 because we don't have source location. So without the file and line, it's basically impossible, I guess. Some of them are really slow to compile because of the implementation itself. So, not ideal, because if you want to scale, you want to compile fast. Some might be hard to integrate because they're not header only. They are libraries. They have to be compiled. They provide CMake or Bazel, whatever, depending on what you need. They might not be part of any system which you have. So they might be hard to integrate. And obviously there are other things which you have to be aware of if needed. So, okay. So that's the problem which I identified with C++ and with the current frameworks. Can we do better? Well, my claim, bold claim, I guess, is that we can with C++20. We can do no macros. We can do a framework without the macros. In my opinion, that's possible, and we'll see how we can do that. And get all the goodies from the framework which you have so far, right? So we'll get the line and number, we'll get the tests with the names and easy registration. All the goodies still. With the minimal boilerplate, that's the premise as well. Minimal learning curve, meaning not a lot of concepts, basically just lambdas and user-defined literals will be enough for us to do the testing. Easy integration. I claim that with the modules and header-only libraries, we can do that very easily. We want to be flexible and scalable as well, meaning we would like to have fast compilation times. We would like to be able to have test suites and thousands or hundreds of thousands of tests, which we'll be able to do. Sorry, I just wonder what I have. Okay. And we also would like to compile and execute really fast. That's always a good thing, no matter what. Okay. So what's the goal here? The goal is to do the same which we've done before, but with the testing framework. What I mean by to do the same, by do the same, I mean let's test this sum function which takes the variadic pack and just sum the numbers. How we can do that with C++20 is shown here. So we have 7 lines of code to do so, and that's what we will try to implement in less than 200 lines of code of C++. So first line, just let me go through it quickly, is to import the module, which we'll try to implement, which will be called DUT, because of the unit testing, as well as micro framework, because it's quite slow. And then on line 3, we'll have the main, because we have to have the main to run something. And on line 4, we'll introduce a UDL_test, which will be testing the sum, and we'll follow with the Lambda expression in which we'll verify the sum that 1 plus 2 equals 42, and we'll expect that to fail. And what is important is that we'll get the line number, which is 5, the file, which is sum.cpp in that case, and the expression as well, which is 3 equals 42, which didn't pass. And after that, we'll get a simple summary of tests: 1 test, 1 failed, 1 assert, 1 failed, out of that. Please notice also that on the line 5, we don't even have to write expect or require or check or anything like that. We'll just leverage the comparison between a comparison operator and UDL on the right side, underscore I, just to compare and get the output. I think that's really expressive. I think we can get testing facility like that with C++20, and that will be great for being really expressive in the long term. So the other goal which we would like to have as well is to have the test suite in which we'll have multiple tests. And on top of that, we'll use expect, because not everyone is comfortable with just using the comparison operators for testing. So that will give us the ability to be more expressive if you want to use expect. So I hope that makes sense. And yeah, let's dig in and try to implement those things. I hope you're excited about this framework and what we can do with C++20. In my opinion, it looks great, and it's a great facility for having primitives to express testing in C++. So as I pointed out, implementation is just, obviously it's simplified, but it's 200 lines of code, pure C++20. Okay, so how we start, how we do actually start with it. Let's say we have this module which we want to do. So that's the first thing which we have to start with. That's the first line. We'll go line by line in order to satisfy all the requirements and achieve the goal. So let's introduce a UTHPP. Since we don't have really a good practice at the moment with the modules, what's the what's the extension? Whether there should be extension or should be like PCM, HPP. But because the UT which we'll try to introduce will share the header onlyness with being a module, if supported, we will just stick with the HPP. And we'll introduce the module interface unit, which will just do export module UT. We'll also import the STD in order to be able to leverage standard facilities from C++. So that will give us, everything we need to print and stuff like that. And for the simplicity, we'll export the full namespace. Modules are great because they allow us to export only required things. So if you have the detail namespace, you don't have to export it. But for the simplicity, we'll just export the full UT namespace. And you also, please notice that we have the version 1, which is the inline namespace from C++ 11. So if you follow that up with the main CPP, in which we'll import the UT and have the main function, doing basically nothing, we can, with Clang, compile that by emitting module interface with the HPP file to a PCM file, compile it, and link it as well into the main. And when we call it, we'll get basically nothing because main is empty. However, as you see, the module will be imported. And since it's empty, no issues there. However, we have the whole module and the first line achieved. So we can move on. So as I pointed out, blue background, something to remember, something to take out of the talk, that modules are great because they're not text replacement like includes, and they have a lot of benefits. But module interface unit is this module which has the export keyword as a first line. So you can think about the modules as precompiled headers kind of thing, and that's the way they are implemented in Clang either way. So they're very similar. However, they have more benefits just than the precompiled headers. At first, you can have multiple of them and combine them together. Secondly, they allow you to hide implementation details, which is not always possible with precompiled headers. Also, if you have a lot of translation units, they'll be much faster to compile than just includes because we won't repeat the same inclusion multiple times. So that's all of that great. They won't help us much with the templated code, but that's fine too. At least we'll get those benefits. So okay, we have that. We have a module. Let's try to implement line 4 then. Line 4 here is a test. A test is a UDL which will allow us to test and execute our tests. Since we have C++20, let's start with concepts. Concepts are important for us to verify whether we will satisfy our requirements for types which we will pass. So our concept test will require a name. We want the name to be part of the test so that we can satisfy this running test, which we wanted to do. Printable means that we have a concept which can be outstreamed to the output. Nothing really special here. We can just clog that guy, for example. We'd also like to be able to assign a lambda to the test. So that's why the equality with the expression is something which we would like the concept to be satisfied on. So for example, if we have the test equals a lambda, this concept has to satisfy that. So that's basically it for the test. We just need a name and just assignability from the lambda expression. So yet again, something to remember, concepts are type constraints. they act kind of like documentation for interfaces, or like with the virtual classes, you could see, but not the same way as you could express with concepts. When you have the virtual functions, you override them. Here, you can just say what has to be provided to for concept to be satisfied. They give us better error messages because they give, the error messages are coming from the point of instantiation, not from the the library code. If you haven't ever seen the STL error messages when you try to when you got a mistake somewhere, that's not what we want. We want the error message at the point of the instantiation, so it will come from the library use case, not from the library implementation. Implementation detail we want to leave alone and from the users. And obviously, they, in comparison to Spinner, substitution failure is not an error. They'll be faster to compile because it's a compiler feature, not enable if kind of trickery with the type trait. So that's great too. And I won't be giving you a full deep down into concepts that a lot of great talks about it already. Just wanted to point out that you can think of them as type constraints on types. So if you have class or type name, if you put something which is more constrained, that will be a concept, and it will give you nicer error messages. So auto, it's the last constraint concept. It's the same like value space auto. If you don't put anything there, it will be just deduced. If you have a concept which is just a true, it will be always satisfied. There are a lot of syntaxes for concepts. We'll probably leverage 80% of them. So I just wanted to give you a quick overview if you don't have them. First one, first line here, auto foo, auto arg, no concept. Basically, auto means that anything has to be anything can be satisfied. So we can think of it like any concept. Cool. We can also requires. We can leverage the requires expression here with the concept auto, which will give us basically the same because the concept is always satisfied. We can do it on the left side or right side, depending on whether we want to leverage the arguments or not. We can also put it instead of class or type name. That's nice too, where we can do it. Not always possible when we want to combine multiple concepts, then that might not be always the case. And we can also use Vister's syntax, which is really nice when we put a concept and after that an auto and after that an argument. We'll leverage, as I pointed out, most of those syntaxes. So just to let you know that all of them are sort of equivalent regarding the concept satisfaction. Okay, so hope that makes sense. Let's try to implement then the test. As pointed out before, they are concept for the test. And I noticed here that we don't inherit from anything because we leverage concept-driven design and not really, object-oriented design. So we don't have to inherit it and do OO, anything like that. So the name is just the string view because it would be taken from the compile time kind of context. Also, we want to have, we also not want to have, we actually need to have the equality operator with something which is invocable, which in that case is the Lambda expression. And what we'll do when we assign, that will be the simplest way of doing it. We'll just log running, we'll log the name and run the test. So I hope that makes sense. That will allow us to execute the test. Obviously, the fully featured framework will not run the test immediately. We'll just store them somewhere, and then when you ask for running specific tests, you would be able to do that. But in our simple 200 lines of code use case, we can just immediately invoke it. And we'll also provide this UDL underscore test. And notice here we'll return a test concept as well. You can use this syntax on the return type. And that will be C++17 here, UDL, which takes the name and the size, and returns the test, in which we will leverage the designated initializers, the dot name equals name and size, to initialize the string view of the name. And the name size is the name of the everything which will be provided in the quotes before the underscore test. So for example, in our case, we'll go to UT, the line 4, sum will be the test case name. So yeah, this code will actually compile right now because we provided the UDL for underscore test, which has the equality operator for the something which is invocable. Invocable in that case will be the empty Lambda expression, which will be executed immediately when assignment will happen, and it will print the running sum. Woohoo! Great, right? We have something already which is runnable, compilable with the module. I think that's already a great progress. So far, I hope you with me on that the previous slide is kind of an achievement already with C++20. Looks pretty good in my opinion, at least. So what will be the next step? Obviously, testing is not just about running tests. It's mainly about verifying expectations. We need those two parts in order to do proper testing. One without another, it's kind of useless. We could deal with just expectations, but having ability to, separate tests, put the test suites, names on it, it's really important as well. So let's try to implement this assertion on line 5. So we have this sum, which takes 1 and 2, that would be 3, but we want it to be equals to 42 because we want the test to fail. We'll have to implement two things here, the equality operator and UDL for underscore I in order to make that happen. And we want this UDL in order to avoid implicit conversions and be explicit on what we will actually compare. And also because otherwise we wouldn't be able to get the nice error message with the line, file, and the expression. I will take a look why later on. So there are a few issues which we'll have to tackle in order to make that happen. First one is that operator overloading in C++ doesn't allow us to overload built-in types. So we cannot do ints and stuff like that. We cannot overload them, what I meant. So for example, we cannot do that. Operators equals int, that's built in because int and end is built in. So we cannot overload that. And that will get us an error message that at least one parameter of class has to be of type class or enumeration type. Well, so that's a bummer already, because if you wanted to write sum 1, 2 equals 42, that wouldn't really work because both of them would be an integral types. And we wouldn't be able to overload it, and we want to overload it in order to get a specific behavior for our use case. However, we can do something like that. We can, as the error message says, we just need one parameter to be of type class, for example. So we can leverage integral constant as one part of the equality operator, and then we'll get that to compile, and we'll be able to overload this guy and get our expectations printed. So let's start with this implementation. We'll have equality operator, which takes left and right hand side, and one of them has to be at least an operator. What does it mean to us? Let's take a look into the concept of the operator as well. Since we are in C++20, we want to leverage the concept-driven design. We do not leverage here for the reasoning different than because it's difficult to show how to do test-driven development whilst you're doing the testing framework. We won't be leveraging that, but we want to leverage the concept-driven design in order to show that C++20 features are important. And if we actually implement an easy framework to leverage C++20 to implement testing, we'll be able to easily and by default implement C++ testing by default. But we're not there yet, so we're trying to get there yet. So let's take a look into this concept. Concept of the operator will require it to be printable because we always want to print. It's a testing framework, so we want to print the left-hand side, right-hand side, the equality, and stuff like that. So we want to store the side, left-hand side and right-hand side operator as well, because we will need to compare them. And they have to be convertible to bool, because otherwise we will not be able to express the result, whether it fails or succeed. There are two different ways of having two different types of operators. Some of them are like equality, when you have the left and right hand side operators. On the other side, we can have a user-defined literals like 42, which just requires the value. I hope that makes sense. The first one is for the more operators which are combined together, like 42 and equals a value, and when you get the equality, which you can also compare later on. And that's what we will just return out of the equality operator, which will overload for the our use case. So let's try to implement that guy. We'll leverage here the deduction guide to get nicer syntax for the future. We'll put the left-hand side and right-hand side as member variables. In the deduction, we'll verify the expression by having the if statement. If since it's convertible to bool, if it's false, we'll error. We'll take a look how it does look in a sec. We'll also implement the conversion to the boolean, which will take the value of the left-hand side and compare it with the right-hand side. And we also would like to be able to print nicely, which means that we'll get the value of the left-hand side, right equals, and the value of the right-hand side, because that we want out of the expression. So I pointed two things here, the error and the value, which we'll take a look into how they can be implemented. So the error, pretty easy. We'll just print to CR failed an expression. Since expression is printable, as pointed out here, it will print nicely the expression. That's awesome. Value is important to get the underlying type of the operator, because when we have the integral constant, it will has the value in it. Otherwise, we'll try to print what we can get if you have the non-operator thing. So for example, here might be a 42. 42 will go to the else, and 42_i will go to the op that value. Hope that makes sense. This pattern here is called if concept requires is, I think, I believe personally, is the best pattern provided by C++20 combined with C++17 and concepts, which is called design by introspection, introduced by Andrei Alexandrescu. And that's something to remember because it's a game changer, in my opinion, in C++20. So if you have, for example, a function foo, and you would like to verify that the object which is provided has actually a foo, a member foo, you can do it without naming anything, naming a concept, or doing a sphere magic or anything like that. With C++20, you can write if consexpr requires v.foo, and if that's satisfied, then we'll go to the first branch, otherwise we'll go to the second branch. And why that's important? At first, if you don't put the consexpr here, that won't compile because both branches will have to be syntactically valid, and therefore the foo, if you provide something that doesn't have foo, it won't compile, and that's part of important part here, that we want it to be always, that always will compile, and it will just behave differently depending on whether the foo is there or not. So let's take a look into the example. When we have a struct which has a foo member, and we static assert on the function foo, we'll get 42 here because it will go through the first branch. If consexpr requires v.foo satisfied, yay, foo.foo is being returned. When you have a bar, when we have a struct bar, when you have a b, which is a struct, anonymous struct, and it doesn't have the foo, it will go through the second branch and return 0. So that's awesome. If you would like to understand more about design by introspection, because that's just part of it, I really, really advise you to watch that talk by Andrei Alexandrescu, because with C++20 we can really leverage it, and it's a game changer. Trust me on that one. If anything, just remember these slides from the start. Okay. So right now we have both things. We have the UDL and we have the equality operator. So that code will compile. Almost, because we don't actually have the UDL. Sorry. We have the equality operator. Right now we want to implement the UDL. I've gone a bit further than I thought we were. So the UDL itself, the user-defined literal, has problems with C++17 and 20 because it cannot be overloaded for all the types easily. It's only supported by the assign long end or long double, but we want to avoid implicit conversions. So we would like to have it for the int, short, and other types. However, that's not possible. So if you try to implement operator for _i, and all of them have to have underscore because non-underscore are already reserved by the standard, we'll get an error that the invalid return operator type int is not allowed, and you have to use the assign long. So that's not ideal. We can't really leverage that one. Sorry about that. However, there's a UDL kind of provided, which we can overload, which just takes the characters. And in that case, we'll have to parse the characters ourselves. But because we use different underscore name, we can do it ourselves and get the proper names as well, proper types. So here we'll leverage yet another game-changing features from C++20, which is the Lambda, familiar template syntax Lambda or something like that. I think that's the way it's called. For the Lambda expression, in which we can immediately invoke function expressions, get the types as well out of it, and expand them using fold expressions. So here we have a Lambda, which will be returned. we'll get the index sequence, great feature from C++ 17. We'll get the Lambda. And the important part here is this angle bracket auto ... ns, which will allow us to use fold expressions. And then we'll have to, as I pointed out, parse it. So we'll have these characters, but we will return an integral constant of type int because it's _I, in which we'll just calculate the decimal number out of the provided buffer, which will be the CS -0, which is 48, ASCII character, and leverage and multiply it by the decimal power of 10. The calculation is obviously quite easy. So, and then we can verify that static assert that 0_I equals 0, 42_I equals 42. So I hope that makes sense. I know it's a lot of code here, which might be, C++ 20, and if you're not familiar, it's kind of, oh my gosh, what's that? But I just wanted, to leverage the C++ knowledge by, we can actually do that, and that's super awesome. And in the future, that would be something which would be really leveraged, because this talk is about the future. So as I pointed out, immediately invoked function expressions is something to remember because it's a great feature from C++ 20. For example, we can do unfold in that way. So unfold would be a great feature for performance reasons. When we do for, and we cannot guarantee that for will be unfolded unless we do pragmas or something like that. By default, it will be a jump. We'll go have a label, do an expression, and after that, jump back. If you want to do unfolded version of the loop, we can do that with this basically one line in C++ 20. We just say how many times in the first line, and we will follow this immediately invoked function expression thing. And call it with the expression on the middle of this code listing, in which we have to do this trick with void is because we don't pass is into the expression. That's just important for the sake of fold expression in order to be able to expand on something. Otherwise, we wouldn't be able to. So if you called unfold2 with, ACCU, just print ACCU 2021, the assembly output, because the output at runtime will be ACCU 2021 printed twice, but from the assembly perspective, take a look that we actually call put twice, and there is nothing else provided. There's no loop. There's no label which will come back when the 2 is satisfied or something like that. We just have the stack, which is for the main and arguments, and after that put the string into the register for puts and call it twice. So that's great, isn't it? Because it allows us to be really expressive with C++ 20. But moving back to the assertion, right now we have _I. And what we'll get? We'll get failed as expected. That's cool. 3 equals 42 because we provided this operator, streaming operator for our expression. It's missing the file and line. And in order to provide that, we have this C++ 20 feature, which is called source location. You are probably familiar with file and line and function from C++ 03. But they macros, and that's why all testing frameworks which are, C++ 17 and below cannot leverage that feature and they have to be C++ macro based. So that's not great. But with C++ 20, we can leverage source location like that. So operator equal. We get 2 things, and maybe we could get a default location argument, but unfortunately, operator equal doesn't allow us to do that. So that's a bummer. Source location doesn't give us that here. So yeah, although it's a great feature, we'll have to work around it a bit to get it done. So how we can go about it? Just to point out how we print the error. If he has to get the proper location, if you get the location out of the source location, current stuff, we'll be able to print the file name and the line, as that's part of the interface. If you read the standard, I didn't point out before, but all the blue backgrounds have also a draft link if you're interested in more details. But you can get line, column, file name, and function name out of the source location. So we'll be able to print the error. So in order to implement that, we can approach it differently, since operator equal doesn't allow us to get it done. A bummer. But instead, we can leverage the constructor of equality operator by providing this default parameter there. However, as you probably will notice in a sec, the file line will be the file and the line of the UT library, not the Colli side. So that will be UT-HPP and, for example, 128, which is not ideal. So if you follow up with this error and pass the location as pointed out, and we will get this assertion, because that will compile and everything seems to be okay. We keep our fingers crossed that it will work. It will. We'll get the file and line. Partial success, the successful operation, but the patient died in the process, I think, because we'll get UT-HPP 128 instead of some CPP 5. Having that line is totally useless for debugging or anything like that. That's why we would have to leverage the macro. But we can go further and hack it more in order to get it done. Let's introduce a value location, which will store the value and the location. There's no much difference here in comparison to the equality which we just had. We still have a default parameter which is provided by the constructor. But the difference is that we'll use it in the equality operator. So the value location will be instantiated for the types. So the types have to match. The value type and the right-hand type will have to be deduced. Will have to be deducible. But because the value location is on the equality operator, it will be instantiated at that time, and the constructor will be triggered, and the source location will be the correct one. So then we can introduce the equality, which will just inherit from the detail equality, and will provide the location from the value location. So we'll pass it to the error. So that's a nifty trick in order to get the source location being passed into the error. Because as pointed out, default argument doesn't work here for operator equal. If we put it inside the LHS, for example, which won't be deduced in the Colli side, we will get the wrong number. But if you follow that trick, we'll get the proper error. So right now, if you go back to the assertion and the equality operator of the underscore IUDL, we'll get the Testcpp. That's the file which I compiled with. Failed 3 equals 42. Yay! So achievement unlocked. I hope you're still around because I don't actually see it. I guess we'll deserve a bit of drink. So yeah, I'm really happy with that. Sorry about that. So first goal achieved. I hope you didn't get lost too much with all of that. But just to sum up, we got quite far with not a lot of code. We got concepts so far, modules, source location, and few tricks with design by introspection, and immediately invoked Lambda's expression as a big winners of C++20, and we are really expressive so far. I believe the code is neat and gives us macro-free testing, which is pretty cool. So right now we would just like to follow up with a test suite, just to be able to get more tests together and combine them into more concise units. We'll also leverage the expect here, because not always equality operator is the best way of doing it. But let's try to achieve that. That will be very simple. We just need expect, and we'll need the test suite. So the expect, which also here leverages the streaming operator, not a biggie, just because we can, will be very simple, because we have expect, which will return a streamable concept. There will be an expression concept followed. And then, since a function, not the operator, we can actually use the source location. The expression itself is something which is printable and convertible to bool. I think not a surprise here. We will also leverage, in case the expression is not satisfied, is failing, our previous error of the expression and the location. Location is taken from the expect, because we have it already here. We don't have to do these tricks with the value location, and we return std error so that we can follow up with the streaming. So the streamable was required for the output. And that's basically it. So the expect is very simple to implement, since we have all the facilities already provided. So how the equality operator will look like in that case? There's actually no changes. It's still the same. Takes either operator on the left or right side, because that didn't change from our perspective. It doesn't have to be the value location anymore. So we have two different overloads depending on what it's going to be passed. So that will allow us to have expect a function which will take the expression inside, and also allows us to do the streamable thing afterwards. And that obviously takes the proper source location. No hackery required here to get it properly. So I hope that makes sense. It's not a biggie follow-up from what we had before. There's also the test suite, which we want to implement as a follow-up. That's super easy. It's just a struct which in the constructor takes something which is basically invocable. That's the suite concept. And we'll just execute it, because we lazy in that simple testing framework from scratch, and we want to execute them immediately. In the proper version, we would store it and execute when requested. So with those two things, we can already leverage another goal. Expect will just work, because even equality worked before. So right now we just have an expression which will be passed to the expect. Source location will be passed into that, and the expect itself was verifying the expression and printed an error if it wasn't satisfied, if it was failing. The test capability to print the names and run, we already leverage. So basically, we'll get the running all the tests as the output, and all of them will pass in that case. So yeah, we got second achievement unlocked very simply. So the second part was to point out that how easily we can leverage these primitives in order to get more things. And by more things, I mean, test suites, expect goals, different benchmarking, parallel executions, and stuff like that. Spec, if you're familiar with that, Gherkin. So yeah, C++ is really expressive. C++20 is really expressive, and you can find the full example and the full code here on that link. You can also find the header version on the Godbolt if you want to play with it, and you can find a module version on the OneBox. All of them are fully implemented in C++20, 200 lines of code, more or less. Tested, and you can easily experiment with them if you desire. But right now, let's take a look into how much we can push that envelope if we just increment this line count to 2000 and see what kind of framework we can actually provide. So that's the second part, the quicker part of this talk, since we spent an hour digging into the implementation of the UT. I hope the UT for you makes sense, and the implementation was sort of easy to follow, because I understand a lot of probably new things if you're not familiar with C++20. But the main point is here that C++20 is awesome. That's the main point. The second part is really expressive, and it gives us a lot of features which can make the expressiveness and code really easy to follow, and let us allow us to implement this awesome framework, which is called UT or micro UT. You can think of it as a competition to popular framework, frameworks such as Catch and others, but you don't have to as well. You can find it on GitHub if you want to take a look. I really encourage you, because I think it's an awesome framework. If your company allows, or your side projects allows C++20, I really encourage to try it out, because in my opinion, it's just awesome. It's awesome not to be forced using macros, and leverages all these C++20 features to get really good code. So just an overview. UT, as pointed out, is C++20. It's supported by most compilers, big three. Some limitations may apply for some compilers, like MSBC 2019 doesn't implement source location fully yet. It's a single header and a module, 2,000 lines of code, no dependencies besides the STL module or headers. It's macro-free, obviously. Woohoo has tons of features, which all other frameworks also provide, does in a C++20 fashion. And it's in a Boost namespace. It's not a Boost library or anything like that. It has aspiration to be in the Boost. It's on the Boost pipeline to be considered as a library at some point. So how does it look? Hello world. You can follow the Godbolt link. Our use case for the sum would be you do import as before, or include. You can do either. You have to write this using namespace to get all these goodies out of the framework, and you can just simply implement the test as before. Notice line 11 also allows to compound statements, which is even better than before, and the error will be in colors as well. Sum CPP 11 failed 3, which is a sum 1 plus 2 greater than 0. That's green because it's true, and that's the expression which failed because 41 is not actually equals 42, as we all know, and therefore we got the failed output, and there's a sum up at the end. So yeah, that's a really nice framework. Colorful, easy to use. How to use it? So the main, we can filter. Like right now, I'll just go through the features quickly because you can easily go online and verify all the features if you desire. I just wanted to point out what we can actually do from C++20 perspective after having this 200 lines of code framework from scratch. If you follow it up because you got excited, oh my gosh, that's like super framework already. What we can do with that? So we can filter tests, for example. So if you have the main and different tests, we can use regex to filter which test we want to pass. So all tests pass here because the main was triggered with a star. Or if you try to run single tests, we can do that as well. Or many.equal, because it's like compound test, like subsection, many.equal or many not equal. Also will pass the one test, which is the many.equal. So yeah, that's very common in other frameworks as well. Just pointed out that we can do that with C++20 and this framework too. We can tag tests, which is very often useful for performance tests, for example. If you tag it by nightly or slow, because we wanted to do something at nightly builds, we can tag them, and we can also skip tests if you want. That's just the tag which is called skip. And we can decide which tag we want to run by override the default config, the .tag nightly. And that will just call the nightly tests. It won't run any other. And also notice that the skip test will be skipped because it's skipped. And skip means that it will try to be compiled, but it won't be executed. The main part is assertions. Assertions are great. They are part of all frameworks, and we have to always leverage them in many different ways, I guess. So here we have third syntax as in our testing framework from scratch. 1 equals 2, failed. We can do expect as well on top of that, which we've seen before. That will give 2 equals 1. We can also have the matching syntax, expect that percent 1 equals 2, which notice that doesn't require the underscore UDL, which is sometimes handy, especially if you want to use the macro to do the trick. That's what most frameworks leveraging. They leverage an operator in which the priority is lower in order to get that done. So matter syntax is one of those guys as well. We can also have fatal assertions, which are related to the fact that you don't want to follow because you will have a segmentation fault if you do that. So for example, if you have a vector and you would like to verify on line 3 that the last element which doesn't exist in that vector will be 4, that would be a segmentation fault. So we want to bail out by default on the line number 2 with the fatal. So that's like requires versus check in catch, I guess. We can also, do the floating point comparison, and notice here that you can get the precision based on how many zeros you put under after the number, because we parse it. So if you compare 41.10_d with 42.101, the precision will be deduced based on the lower part. How many numbers actually they were used after zeros. So we can do 10000, and that will be the precision which is required. You can also specify that explicitly if that's kind of dodgy or you don't feel comfortable with that. You can also compare the strings or other types or custom structs. There's no issues with stuff like that. We can get the colors. All of that is supported. You can also do login. So you can log an expression, like in Google tests. You can also log it with expect, or you can just print log if you want to, have the steps being logged in the lesson if you try to debug something. You have sections. Catch popularized them, and I think they're awesome. They're really easy to implement with the Lambda expression kind of thing. You can, look at them like something like we have a test vector which will be executed once, and after that we have a setup. We don't have to, like in Google Test, you have to do the setup function and stuff like that, which you don't have to. You just follow up with the code. The setup will be done once here, but it will be once. One will be done once per section. So if you have the shoot, the setup will be done first. After that, the section, shoot section will be done, in which you can verify your expectations. Notice the mutation here because we pass it by copy and want to modify it. You can also do it differently. I won't get into details. And after that, this expression will be followed. And when we have second subsection, it will go from the beginning. So it will do the setup. And after that, we'll avoid the shoot, section 2.1. We'll go to the verification on the free part and section 2.2, and then the teardown. So it's like a subsection in Catch. You can also do test suites. As pointed out before, we actually implemented them. So you can throw, you can do abort verification on Linux. You can just, make the test concise if they have should follow up the same kind of patterns. You can do parameterized tests, which is like extremely, a game changer for frameworks like that, because you can do that with for, actually literally a for loop and have a test which you put a name on at runtime and add expectations. That's quite difficult to another framework to do. The same kind of thing you can do with more declarative version with piping to do a tuple, for example. When you get types as well, you have all the leverage here to do type metaprogramming or simply for as well. You can verify also the template metaprogramming with this framework by using constant, and you will still get nice error message that this context per value I doesn't actually equal, which leverage the NTTP non-template type parameters from C++20 in the implementation. We didn't take a look into that, but that's something which you can take a look afterwards if someone desires. You can easily implement a spec with this framework. Can leverage Ruby on arrays functionality, and instead of should or test, you can have describe it, same thing. We can have behavior-driven development as well with the feature, scenario, given, when, then. All of them, like feature, scenario, all of that is implementation detail, which is just a Lambda expression. It's like should, which is implementation of it is just a Lambda with a different name. That's it. So all of that leverage the same backend. There's no much logic here to express, but you can see that it's very simple to do, and there are no macros still. UT also support the Gherkin. If you like Gherkin and BDD, you might really like that, because that allows you to express the feature test in a separate file and backend, and just use the UT as a backend. That's often the case with, for example, Behave in Python, or Gherkin is supported by all the platforms basically. So having it in C++, it's awesome, great, because you can have the one implementation of business requirements provided you by the product owners, for example, and then just implement them using different backends. So in C++, leveraging library features, or in Python, leveraging binary end-to-end features provided. So when you have this feature, which is the same kind of implementation as we had here, just instead of C++ being explicit in C++, we have an external file which we leverage. And then there is a parser, and we just implement the steps instead. And the steps are following the implementation of the requirements for them. So if you have the parsing part here, we can implement the step. I won't be going into details how to do that if you're not familiar with Gherkin, but you can imagine that instead of having them explicit in code, you write kind of the parsing steps, and then they will be executed accordingly to the test file. So you pass the steps which you implemented into the file, which is being read by underscore file, UDL, and all the tests will be executed. So since we don't have that much time, let's just get through the parallel execution and a few more features. I hope I'm not going too fast. I just wanted to point out that UT is awesome. So a lot of features to check out probably yourself afterwards if I'm going too fast. But you can here just to point out that UT is really flexible. It has you can change the reporters, printers, and anything you actually want with this framework just by overriding a variable template. So, for example, if you implement parallel runner, you can very easily run the test in parallel. There's like 5 lines of code to do that with parallel for execution, which is actually provided in the link if you want to follow it up. That will allow us to run tests in parallel out of the box. You can also do benchmarking very easily as well with underscore benchmark. We'll just leverage this do not optimize in order to invalidate the cache, and we can get out of Godbolt a number, also link provided. So yeah, there are much more features, and sorry for going probably a bit too fast, but all of them can be verified on the GitHub. I hope I get you excited about UT and not discouraged. It's super awesome in my opinion, but I'm obviously biased because I implemented it. But yeah, not having macros and being able to express features so easily, all of that is 2,000 lines of code, makes all the difference. C++ 20 is awesome. That's all the theme of this code, and that's the future of testing in my opinion. So let's take a look into the benchmarks quickly, because I claimed that I'll provide them. So we'll just provide different frameworks. I try to, it's really difficult, disclaimer, to compare apples to apples. So I don't want to claim anything out of those benchmarks. I just provide the numbers. And I try to use the frameworks as they are advised and advertised. So if it's advertised as a single header library, that's the main thing I've taken for the testing. Or if the configuration says for the fast compilation, use that, like I just leverage that. But I didn't get into, oh my gosh, I want to tweak this framework as much as possible to get the results I would like. And the same with the UT. UT just single header, single module out of the box. No, I didn't try to tweak it for no reason. So the include, you can see that catch is slow to include, so you'll pay for that. Everything else is quite fast. When we have a benchmark which leverage 10,000 tests, 20,000, 10,000 tests, 20,000 asserts, and 100 CVP files, and we implement it and we compile it from scratch with asserts and STL included. That's the results. The compilation, UT and doctors are fast to compile. Others are a bit slower. Execution, boost test and catch are quite slow to execute. And the binary size, which is sometimes important, boost test and Google test are big in comparison to others. But I think that's the main outcome from that test. Incremental build is, I think, the most important part of testing because that's where you spend the most time for the one CP file with a lot of tests. The compilation, which is important in that case, and the lower is better. UT and doc test and catch are not that bad. Google test and boost test are a bit slower to compile. Execution, UT is the fastest. Google test is really fast as well in that case. And the binary size shows that the boost test and Google test are having a big file size. And lastly, I also compared the headers versus precompiled headers versus modules. Since modules are implemented using precompiled headers in C++20, you can see that they're much faster to compile than the header itself. So that's good. But there's not much difference between precompiled headers and the modules because they are implemented with the same thing. So that's good. I think that's important to point out. So just to sum up, because we spent a lot of time going through it, I'm sorry about it because we won't have a lot of time for questions, but I promise I will answer as many as I can, and I will also answer them afterwards. So I think as I pointed out, the theme behind this talk is that C++20 is great and enables a cleaner design and implementation. And I hope that the concepts, modules, source location shown that we can leverage those features to get really good design. UT, I believe personally, obviously I'm biased, it's an example of cutting-edge unit testing framework, which is great because we never had that before. We couldn't do that. Something to consider when switching to C++20. Should be possible standardize unit testing primitives, such as underscore test or expect? That's something to discuss, maybe. There are strong opinions in the community whether that should be done or whether that should be a package, external package, which could be provided by external package management. If you get to that, maybe we can have a module which provides that easily in the future. That would be awesome too. There are options here which might be considered. And finally, what about if you have these primitives, can we actually leverage them to build macro-based frameworks? I promise Catch 2 implementation. Let's take a look. You can actually check it out on Godbox. So exciting slide. I promise no macros, but for this slide, let's make it happen with some macros. So require macro, test case, and section might be implemented very easily. And I don't know, if you are Catch 2 fans, you're probably familiar with that syntax. Yeah, so that's the Catch 2 simple, very simple implementation gets to is way bigger than that and has way more features. And I encourage to use it. Obviously, Phil did a great job. I don't want to discourage anyone. I just want to point out that with C++20 and UT, catch2 frontend might be implemented easily with these 3 lines of macros, and yeah, you get very similar syntax. So, for example, if you would like to switch to C++20 and need to and would like to use UT framework, but you used to use catch2, you can do that in steps. So yeah, that will be it. I hope you enjoyed that talk as much as I was enjoying giving it. I hope you learn something out of it. And I would like you to leave with the message that if you like it, then you should put underscore test on it. Always follow the Beyonce rule. And just for people who are enthusiastic about modern C++ features and modern C++ development, QuantLab, the company QuantLab Financial, which is the company I'm working for, is hiring. They have tons of options, and we leverage in C++20 and beyond on a daily basis. So if you're interested in that, feel free to apply on the quantlab.com careers. And right now we have exactly a few minutes for questions, I guess, right now. So I'll just take a look into the Q&A. If I can. I don't want to go here. Slide 14. Why is expression a template parameter and not using a callable concept in the requires? Why is expression? Right, because invocable cannot be part of, like, it's really difficult. Concepts are great, but it's really difficult with concepts to on the requires clause to put a concept in it. So you cannot say requires invocable EI, and after that say that has to be satisfied. So you have to have something which is kind of callable, and that's the Lambda, which is callable, and then you can verify that it will be satisfied or not. I hope that makes sense. But yeah, I think it's just concept syntax. I'm confused by using operator for LHS urges operands, intentional or naming back. Intentional. I don't know where the confusion comes from. How to actually answer that question. Sorry about that. It would be nice to see feature-wise comparison with Google Test. Agree. Not provided though. A lot of features provided by UT already, by Google Test already in the UT. But yeah, there are features which are missing, and there are features which are provided by UT, there are features which are provided by Google Test. Which compiler can be used with UT at the moment, and whether it's released? Yes, it is released. All 3 big compilers are supported. So GCC, Clang, and MSVC are supported. There's a version being released, 1.1.8, which is on GitHub. I found UT on GitHub. It looks to be based on Boost. No, it's not based on Boost. It's just in the Boost namespace in order to be able to go through the review. But besides that, there's nothing related to Boost. There's no Boost requirements or anything like that. It's just leverage the Boost namespace, but it's not associated with Boost in any shape or form besides the fact that it was proposed to be reviewed and might be in the future. What about elapsed time of unit tests for performance monitoring? Yeah, that will be available. Hard to say exactly the options. UT is not coupled to anything, so reporters, runners, everything can be changed. Benchmark can be easily implemented. Underscore benchmark is actually an example implementation of runner in the UT. It's the same, the parallel execution in like 10 lines of code. Main point being, UT is very flexible. It's just really decoupled. Everything can be overridden. All types can be changed. That just a few concepts have to be satisfied, like run or execute. I guess that's it regarding the Q&A. There's also chat. Ooh, a lot of stuff here. I don't think I would be able to follow that right now because I'm over the time. So I guess we can stop here, and I'll try to answer all the questions on Discord. Thank you very much again. I hope you're encouraged by UT and C++20. Really looking forward for your feedback. And yeah, enjoy the conference and thank you.